Welcome to the Complete Technical Roadmap for Data Structures and Algorithms, often abbreviated as DSA. Whether you're a beginner or looking to strengthen your foundations, this guide will walk you through every essential concept, step by step. Mastering DSA is crucial for excelling in technical interviews, optimizing code, and building efficient software. In this video, we'll start from the basics and gradually move towards advanced topics, ensuring you have a clear understanding of each building block. Let's begin our journey by understanding the prerequisites and why a strong foundation in programming is vital before diving into DSA. Before you can tackle data structures and algorithms, it's essential to be proficient in at least one programming language, such as Python, C++, or Java. This foundation allows you to implement and experiment with DSA concepts effectively. Key programming fundamentals include understanding variables and data types, mastering control structures like if-else statements and loops, and knowing how to write and use functions. You'll also need to be comfortable with arrays or lists, pointers, or references depending on your language, and basic input-output operations. These skills are the backbone of every algorithm you'll encounter. Variables are the basic units of storage in any programming language, and data types define what kind of data a variable can hold. Understanding the difference between integers, floats, characters, and strings is fundamental. This knowledge helps you choose the right data type for your problem, ensuring efficient memory usage and correct program behavior. As you progress, you'll see how these basic concepts are used in more complex data structures and algorithms, forming the groundwork for everything that follows in DSA. Control structures, such as if-else statements and loops, allow you to dictate the flow of your program. They enable decision-making and repetitive tasks, which are essential for implementing algorithms. For example, loops are used to traverse arrays, while if-else statements help in branching logic. Mastering these structures is crucial, as they are the building blocks for more advanced algorithmic patterns you'll encounter throughout your DSA journey. Functions help you organize code into reusable blocks, making your programs modular and easier to maintain. Understanding scope, where variables and functions are accessible, is vital for avoiding bugs and writing clean code. Functions also play a key role in recursion, which is a fundamental concept in many algorithms. As you move forward, you'll see how functions and scope management are essential for implementing complex data structures and solving algorithmic problems efficiently. Arrays and lists are fundamental data structures that allow you to store collections of elements. Arrays provide fast index-based access to data, while lists offer flexibility in size. Understanding the difference between static and dynamic arrays, as well as how memory is laid out in row major order, is crucial. You'll frequently use arrays and lists for storing and manipulating data in algorithms, making them a cornerstone of DSA. Pointers and references are advanced concepts that allow you to directly access and manipulate memory. In languages like C and C++, pointers are used to reference memory addresses, while Java and Python use references. Understanding these concepts is essential for working with dynamic data structures like linked lists and trees. They also help in optimizing memory usage and implementing efficient algorithms. Basic input and output operations allow your program to interact with users and other systems. Reading data from the user and displaying results are fundamental skills. Mastering I/O is essential for testing algorithms and handling real-world data. As you progress, you'll see how efficient I/O can impact the performance of your solutions, especially when dealing with large datasets. Analyzing algorithms is about understanding how they perform in terms of time and space. Time complexity measures how the runtime grows with input size, while space complexity looks at memory usage. Big O notation is the standard way to express these complexities, with common forms like O1, ON, and ON2. Learning to analyze algorithms helps you choose the most efficient solution for a given problem. Big O notation is a mathematical way to describe the upper bound of an algorithm's running time or space requirements. It helps you compare different algorithms and understand their scalability. For example, O1 means constant time, ON means linear time, and ON2 means quadratic time. Mastering Big O notation is essential for evaluating and optimizing algorithms. In analyzing algorithms, it's important to consider their performance in the best, average, and worst-case scenarios. This helps you understand how an algorithm behaves under different conditions. For example, searching for an element in an unsorted array could be fast if the element is at the beginning, best case, average if it's somewhere in the middle, or slowest if it's at the end, worst case. This analysis guides you in selecting the right algorithm for your need. Auxiliary space refers to the extra memory an algorithm needs beyond the input data. In-place algorithms use minimal extra space, making them more memory efficient. Understanding the difference between these concepts is crucial for optimizing both time and space in your solutions. Efficient algorithms often strike a balance between speed and memory usage. Arrays and matrices are used to store data in a structured way. Static arrays have fixed sizes, while dynamic arrays can grow or shrink as needed. Matrices or 2D arrays are essential for representing grids and tables. Understanding memory layout such as row major order helps you write efficient code. Common operations include traversal, insertion, deletion, searching, rotation, and advanced techniques like prefix sum and sliding window. Strings are sequences of characters and are fundamental in programming. Understanding how strings are represented, the difference between mutable and immutable strings, and character encoding like ASCII and Unicode is essential. These concepts are the basis for many algorithms, including searching, pattern matching, and data manipulation. Working with strings involves a variety of algorithms. Common tasks include checking for palindromes, detecting anagrams, basic pattern matching, and counting character frequencies. Mastering these algorithms will help you solve many real-world problems, from validating user input to searching for patterns in large texts. Recursion is a technique where a function calls itself to solve smaller instances of a problem. Understanding base conditions and how the call stack works is crucial. Recursion is widely used in mathematical problems, tree traversals, divide and conquer strategies, and introduces you to backtracking. Mastering recursion opens the door to solving complex problems elegantly. Searching algorithms help you find elements in data structures. Linear search scans each element one by one, while binary search efficiently finds elements in sorted arrays by repeatedly dividing the search space. Modified binary search techniques are used for more complex problems. Understanding when and how to use these algorithms is key to writing efficient code. Sorting is a fundamental operation in computer science. Comparison-based algorithms like bubble sort, selection sort, and insertion sort are easy to understand but not always the most efficient. Merge sort and quicksort offer better performance for larger datasets. Non-comparison sorts such as counting sort and radix sort are used for specific scenarios. Understanding time and space complexity, stability, and whether an algorithm is in place or out of place is essential for choosing the right sorting method. Linked lists are dynamic data structures that consist of nodes connected by pointers or references. There are several types: singly linked lists, doubly linked lists, and circular linked lists. Key operations include insertion, deletion, traversal, reversal, and cycle detection using algorithms like Floyd's. Linked lists are foundational for understanding more advanced structures like stacks and queues. Stacks are linear data structures that follow the last in first out LIFO principle. They can be implemented using arrays or linked lists. Stacks are used in expression evaluation, parenthesis checking, managing function call stacks, and backtracking algorithms. Understanding stack operations and applications is essential for solving a wide range of problems in DSA. Queues are linear data structures that operate on the first in first out FIFO principle. There are different types, including simple queues and circular queues. Queues are widely used in scheduling, buffering, and breadth-first search algorithms. Understanding how to implement and use queues is a key skill for any aspiring software developer.